So let's look at this last example because this is a little twist on how we find c. Sometimes we've just got to drop back and punt and do the best that we can. This says the third Maclaurin polynomial for sine of x is given, and it's x minus x cubed over 3 factorial, so we don't have to build it. It's given to us. Use the Lagrange form for the remainder to Taylor's remainder theorem to approximate the sine of 0.1, or 1/10, by this third degree Maclaurin polynomial evaluated at 0.1, and determine the accuracy of the approximation. So remember the things that we need to consider: what's the relationship between x and a, what's the max that c can be that will give us the maximum error. So let's find r sub 3 of x, and then we'll plug in our a value, x value, or some value in between. So we have the third degree Taylor polynomial. R sub 3 says we're going to find the next derivative. We're going to evaluate it at this value c. We'll have to divide by 4 factorial, and then we'll have x minus a, which for us a is 0, to the 4th power. So a is 0. How do I know a is 0? Because I can look right here, and I don't have x minus anything. I just have x and x cubed. That tells me I'm built at 0. Additionally, they tell me that I'm dealing with a Maclaurin, so they tell me a is 0. And here, x is 1/10, or 0.1. Now, I turn it into fractions because lots of times when you're dealing with Lagrange error bound, you don't have a calculator. So, 0.1 and 1/10 are the same thing. So we're dealing with the case that this is the relationship between a and x. And we know that the sine function in the plane behaves like this. And so from 0 to 1/10, wherever we are along in here, that f of x is strictly increasing. But we're still going to have to pay attention to, from the 4th derivative, are we in the numerator or denominator with c? So let's find the 4th derivative. So for our function sine of x, the only way to get to the 4th derivative is to go through the first 3. So the fact that they gave us the polynomial is helpful, but we still have to find those first 4 derivatives. So the derivative of positive sine is positive cosine. Then we have negative sine. Then we have negative cosine. And then we're looped back around to positive sine. So here is the 4th derivative in x. We are going to use the 4th derivative in c. So it turns out that our function is the 4th derivative. So the behavior of our function turns out to be really important here. So we'll go back and we'll say r sub 3 of x is the sine of c over 4 factorial times x to the 4th. And what thereafter is, and I'll write it as 1/10, is the sine of c over 4 factorial 1/10 to the 4th. And I'll go ahead and show you why I change it to a fraction. This is 1 over 10 to the 4th. So if I don't have a calculator, that's going to be much easier to deal with. As a matter of fact, let's clean it up one more time. I have the sine of c over 24 times 1 with, let's see, 10 times 10 times, that's 4 zeros, right? So there we go. So the sine of c over 24,000. Now I want the max output from the sine of c, where c lies in that interval. Well, I know we have a strictly increasing function, and I know that the right endpoint, since I'm not in the denominator of a fraction, is going to be the maximum error. And now we're pretending that this is a non-calculator active question. So do you notice anything? Let's look back up here. We want to know the error between the third degree Taylor polynomial at 1/10 and the output of the function at 1/10. Well, frankly, if I could find the output of the function at 1/10, why on earth did I build a polynomial to approximate it? This is really not that helpful. So this is where we may have to kind of think outside of the box. And we're after the maximum that the error could be. So let's talk about the behavior of our function just as we know it. And sometimes we have to do this kind of thing. And we just, we can't help that. That's just the way it's going to be. I can't find, without a calculator, the value of the sine of 1/10. Unless it's an exact value, I really don't know the output of the sine function. Here's what I do know about my sine function. Its domain is from -1 to 1. Well, I can drop everything to the left of 0 because I'm really only concerned about what's happening between 0 and 1. So I just really don't know. I said domain. I'm sorry, I meant range. Output values is what we're after, right? So I'm really only concerned about the output values between 0 and 1. And I know that the domain values that are going to give me that are 0 to pi over 2. And so on that interval, and I recognize pi over 2 is much bigger than 1/10, but on that interval, what is the maximum value that the sine of c could be? And the maximum value that it could be for any input value is 1. It will always be less than or equal to 1. So, because I really don't have any choice, what I'm going to do here, since I can't find the sine of 1/10, is I'm just going to replace the sine of c with 1. The max error, because the max output of the sine function, is, so I'm replacing the sine of c with the maximum it could be based on my knowledge of functions, and these trig functions, is 1. That's the best that I can do. So sometimes we do have to get a little creative with things, and like I say, kind of think outside of the box. It happens most often when trig functions show up, but I'm not going to say that's the only case that it would happen. But so Lagrange error bound is not that complicated. We just got to sometimes get creative about C, and all the time we have to think critically and problem solve about how our value of C is going to give us the maximum output value for this error bound. So that's all for the lessons, and come to class next time and we'll work some Lagrange error bound homework problems together.